Hello everyone. So guys, welcome to GATE Wallah Aerospace. Guys, my name is Vinod Kumar Datusliya, and I'm going to teach you part of the applications of thermodynamics and propulsion subject in GATE Aerospace. So we have launched our GATE Aerospace branch this year. So those students who are appearing for GATE maybe in 2027 or 28. For you guys, we have already started our dedicated batch for GATE Aerospace preparation. And guys, today I'm going to take a session on the propulsion, where we are going to discuss about one of very interesting topic that is the nozzles. So those of you who are targeting GATE 27 and 28, guys, you can join our paid courses where we will be taking all these all the subjects for the GATE. Before starting, let me give you a brief introduction about myself. So guys, my name is Vinod Kumar Datusliya. I have done MTech from my name is Vinod Datusliya. I have done MTech from ISC Bangalore. Okay, from ISC Bangalore. I was All India rank 1 in GATE Mechanical, so I am AIR 1 in GATE. Okay. Then I have also secured rank 3 in ISRO. Though I did not join Indian Space Research Organization, it was my dream, but I could not join because when my joining, I got my joining at that time. I was pursuing my MTech in aerospace in ISC Bangalore, and extension was not provided to me, so I could not join ISRO. But then I joined General Electric, which is called as GE, and there I was in GATE Aerospace, where I have worked on the compressors of gas turbine engine. I have designed a few of the compressors of gas turbine engines. I have worked on LEAP 1A, which you might have heard the name of. I have also worked on G9X engine, which is one of the largest engine in the commercial airline industry. So after this, I have been associated with GATE Wallah as well, and I'm going to teach the propulsion part of the GATE Aerospace. So guys, today we will start with the first topic of our series on YouTube, and these are the topics which are brought to you by GATE Wallah channel, and through these videos you can get to know that what is the quality of content that GATE Wallah is going to give you. So without wasting much of time, let's start with the first topic, that is the nozzles. So guys, this is the topic which is the core of propulsion. So you might have heard about when we think about aerospace, most of the students or most of the people, those who doesn't know about aerospace, and when somebody says aerospace, there is always a picture in the mind that there is one rocket which is going like this, and this is what everybody talks about. So when we want to know what is the device that actually propels the aircraft, these are called as rockets or probably aircrafts. So what is how do we generate the force which propels the vehicle out of maybe atmosphere, or what is the mechanism by which the thrust is generated or the force is generated? So guys, we are going to discuss about all this, and in center of all this is one of the most important thing which actually develops thrust, and that is called as the nozzles. So when we talk about nozzles, I'm sure you guys might have already seen what does a nozzle look like. So if we talk about in a very layman's term, when we ask somebody what a nozzle is, probably those people who are not from the aerospace background, they will say, okay, nozzle is something which increases the velocity of a fluid. You might have heard that firemans are there. So firemans, they have a nozzle through which they direct the water on the fire. So most of the people, those who are not associated with with aerospace, they will probably say that nozzle is something like this, which is used maybe in the fire main or the fire hoses, through which the water is sprayed onto fire. So this is what everybody says. But if I want to understand from the physics point of view, what is the mechanism that is governing this nozzle? Why the water that is coming out of the nozzle, which you see over here, let's say we have a building which is having a fire. There is a fire which is over here, and this is probably let's say 100 feet tall building, and somebody who's standing over here, a fireman who's standing over here, he has a hose in his hand, and probably he would be directing one jet of water, and through that jet the water is getting sprayed over here. So when we want to talk about that, so can you tell me, or what comes in your mind, that what must be happening over here? So the first thing that comes into the mind is probably the projectile motion, that the water is released from here at very high velocity. This water is released at high velocity, and then it is following a trajectory which is called as the parabolic motion, or projectile motion. So water is sprayed onto that fire. But we don't want to understand that what is happening in this flight region. No. First, we have to understand what happens at the point where the water is coming out of that fire hose. So if we see that fire hose, the fire hose is actually providing the water which is coming out at very high velocity. So if we talk about the basic principle from the physics, can we understand that the water which is coming out from the fire hose is coming out at very high velocity? So can we say that any device which is placed over here and which is let's say generating the water at very high velocity, that some device will be there? But if you see the actual arrangement, so in the actual arrangement, you will see that there will be a pump over here. That pump will be taking water from somewhere. So it will be sucking water from somewhere. It will be pressurizing that water to very high pressures. So if you might have seen a fire hose is always very stretched. If you try to put up, let's say your hand, or if you want to stand on the fire hose, you will see that the fire hose will not bend. It will remain stiff as if it is solid. That solidity or that firmness is provided because the water which is going inside is at very high pressure. So water is at high pressure over here. And you see this high pressure water, when it is coming out of the fire hose, it is having very high velocity. So if we talk about nozzles, nozzles are actually the physical devices. Nozzles are actually the devices which converts. These are the devices which are called as nozzles. Probably you see the nozzle is starting from here, and this device in the blue is what is the nozzle. What is called as a nozzle. Okay? So nozzles are basically the devices which primarily converts very high pressure fluid into a very high velocity fluid. Okay? So if we want to understand what a nozzle is, if we want to see, or if we want to have a definition, formal definition of a nozzle, nozzle is a device, okay, which converts high pressure fluid into a high velocity fluid. Okay? And how does it do? So we are going to see what is the mechanism of this conversion of high pressure into high velocity. But if we talk about nozzles, nozzles basically convert pressure energy. They convert pressure energy into kinetic energy. Now, what do you mean by pressure energy and kinetic energy? So guys, we are going to see both of these terms. So when we are going to see the detailed course on the propulsion, for propulsion, you will require basic thermodynamics beforehand. So Shivam sir is going to take basic thermodynamics. He is going to teach you basic thermodynamics in one of very fantastic way, and from there we will take up the propulsion part, and then we will build up all the concept of propulsion after the thermodynamics. Okay, so pressure energy is getting converted into the kinetic energy. This is what is the main aim of a nozzle. Okay, so when we talk about the nozzle, so you have already seen that in case of fluid mechanics, most of the time we talk about liquids. Okay, but nozzles are not the devices which are only used for liquids. So when we talk about fluid, I hope everybody might have heard that fluids are classified into two categories. For fluids, one is called as the liquids, which are the substances which cannot be compressed, or these are incompressible substances. And we talk about the second class of fluids. Everybody understands? It's gases. Okay, and gases, the basic difference between the liquids and the gases is the compressibility. We cannot compress these substances. So these are called as incompressible substances. These are incompressible. We cannot compress them. You cannot reduce their volume. If they have a specific mass, the volume is more or less going to remain constant, even if you change the temperature of these substances, or even if you change the pressure of these substances. But if we talk about the gases, these are different. These are the substances which are compressible. And what do you mean by compressible? When we say compressible, that means their volumes can be changed with variation of pressure. So let's say if you have a gas of this much volume and it is kept at certain pressure. If you increase the pressure on this gas, if you increase from overall, if you see, if from every side, if you apply a pressure and then you increase that pressure, you will see that the volume of gas might shrink. Final volume might lie like this. So the volume has reduced. So when the volume has reduced, you see this is what is called as compressed. So this gas has been compressed, and this is what is called as compressibility, the ability to compress. So this characteristic is displayed by gases only. Okay, though liquids have very limited compressibility. When we apply extreme high pressures, liquid also compress, but by a very small value. But if you see the gases, they can be compressed to lot more changes. A liquid which might be having a density of 1 kg per meter cube might have a density of 1000 kg per meter cube. That could be the compressibility. That could be the range of compressibility. So these are the two substances that we have for our fluids. But if you see the nozzles, both fluids are used in the nozzles. So when we talk about a nozzle is used for liquids also. Nozzles are used for gases also. But the purpose of use of nozzles in liquids is slightly different, and the purpose of use of nozzles in gases is also different. Okay, both are used for different purposes. Like one of the use you might have already seen that in case of fluids, in case of liquids, firemen's use for spraying of water. Similarly, if you see the gases, where have you seen the use of gaseous nozzle? You might have seen on the workshops where the people go for washing of their cars or the service of their cars. You might be seeing that there is a hose which contains air at very high pressure. So these people, those who are the servicemen, they would take that hose and then they will press one maybe the lever of the nozzle, and you see that the air comes at very high velocity, and that is used for, let's say, removing the dust from the car, or if you open the bonnet, they spray the air so that whichever or the dust particles are there, they are actually removed. So there are a lot of applications where the nozzles are used. Okay, so guys, now you might have got a fair idea of what a nozzle is. I'm sure you guys have studied nozzle in your college also. Okay, but in case if you have not studied, not a problem, because now you can understand what a nozzle is and how does the things work. Okay, so nozzle, we have seen the main aim of a nozzle is to convert pressure energy into kinetic energy. And when we say pressure energy into kinetic energy, what do you mean by kinetic energy? If we talk about kinetic energy of a substance, let's say a substance is there which has a mass of m and it is moving with certain velocity v, then what is the kinetic energy of this mass? You see that the kinetic energy is half mv square. So this is the kinetic energy. And when you see kinetic energy, what do you mean when we say that a substance has a kinetic energy? When we say a substance has a kinetic energy, that means this fluid or this particle is moving with certain velocity. And how is that velocity important to us? We are going to see that. Okay, how the fluid which is having a velocity is useful to us. That is useful to us because when we say the Newton's law, you might have heard the Newton's first law, the Newton's second law, Newton's third law. So again, when we are going to take up the subject, or when we are going to take up the topic of thrust, at that time I'll tell you how this velocity is important in developing the thrust. So you might have heard that from the Newton's second law, force is directly proportional to rate of change of linear momentum of a body. So if the linear momentum of a body changes, that means a force is being acted on that body. So even if a gas which is traveling, let's say it was traveling at a velocity v1, and after a certain time it starts traveling at a velocity v2, you will see that there is a momentum change. If there is a mass m and it is traveling with velocity v1, finally if it moves with velocity v2, you see that the momentum has changed. And when the momentum has changed, how come the momentum has changed? The momentum has only changed because there is a force which has been acting on this body. There is a force which is acting on this body, and that force we measure by the change in linear momentum of the body. So if you see this is the force, what will be the force? Force will be directly proportional to rate of change of linear momentum, that is mv2 minus v1 divided by some delta time t, that we are going to see later. So you see the force is coming directly from the change in velocity. And from the Newton's third law, you see that every action is equal and opposite reaction. So when there is a force which is acted on this fluid will also generate, or it will also apply a force on the object which is applying a force on this fluid. So every force is equal, or every action is equal and opposite reaction. So you see there will be a force applied on the body which is applying a force on this fluid, and this is what we actually called as the thrust. So if there is a high velocity jet which is coming out from an aircraft, that means some force is applied on this jet, and in return this jet will also apply a force on this aircraft. That is what we call as thrust. But this we will study later probably, because we cannot study everything in one go. So again I will summarize it to you. When we say change in kinetic energy, nozzles are used for converting, or they are used for converting pressure energy, I will write PE. This is not potential energy, this is pressure energy into kinetic energy. And what happens when the kinetic energy is increased? When the kinetic energy is increased, when the kinetic energy goes up, the velocity goes up. Velocity goes up. And when the velocity goes up, you see that the momentum goes up. And when the momentum goes up, that means a force has been applied on that fluid. That means there is a force applied on this fluid in the upward direction if the velocity is changing in upward direction. And because of that, there will be a thrust that will be generated. So you see, when the nozzle increases or it converts the pressure energy into kinetic energy, that means it accelerates the fluid. It applies a force on the fluid. So when there is an application of force on the fluid, its velocity increases. So velocity of fluid increases, and velocity of fluid, when it is increased by the nozzle, there will be a thrust applied on the nozzle. So the thrust will be applied on the nozzle by the liquid or by the fluid, and that nozzle is connected to aircraft. So you see, this is how the thrust is generated in an aircraft. Okay, so today we are going to see how a fluid is actually accelerated. What happens inside the nozzle? What is it that accelerates the fluid? Okay, so to understand the concept of how does the acceleration happen and what is the amount of thrust that will be generated. So before moving on, we have to understand what are the governing equation which actually governs the functioning of nozzle. Okay, so we have to understand what governs the nozzle. Okay, and when we talk about nozzles are actually used with two fluids. So one is the liquids and other is the gases. So liquid part we are not going to study over here, because liquid would be taken up in the fluid mechanics case or in the fluid mechanics subject. Here we are going to study about the gases. So what happens when the gases pass through a nozzle? Okay, so to understand what happens in a nozzle, first we need to understand what are the shapes of nozzle and how the shapes are arrived at. So to understand the shapes of nozzle, how the nozzles have come up, we have to go back again to where the nozzles have actually been invented from. So nozzles have actually been invented from liquids. Okay. So first we will see what is the governing equation for nozzles in case of liquid. Okay, so to understand the governing of nozzles in case of liquid, let's first understand what happens in fluid flow. So when we talk about the fluid flow in liquids, okay, so let's talk about fluid flows in liquids. Okay, so let's say I have a duct. I have a simple duct. Everybody might be having a hose at home. So you might be having a hose which you connect to tap, and from that tap there is a water which comes in the hose, and let's say this hose is a constant area hose, or we can call it a duct. So you have a constant area duct. Okay, and the area of this duct is, let's say the cross-sectional area is A. The cross-sectional area of this duct is A. Now let's say you have certain amount of water which is coming or which is entering at this location. Let's say this location is location 1, and this location from where the water is coming out is location 2. Okay, and this is a hose which is not leaking. There are no cuts, unlike your home hoses where somebody where this hose might have cracked over here, and then you might have put a polythene over it, and then you might have wrapped sellotape over it, and then every time when you switch on the tap, you see that there is some water always coming out of this hose. You might have always be wondering why it happens that even after putting so much of sellotape and so much of polythene, the water is still coming out. It is because of the pressure which is there inside this hose. Okay, so if a hose cracks, there are always some gaps which are kept, or there are always some gaps which are left when you wrap that polythene over that hose, and there is always some water which is coming out of that. Okay, so let's say this hose is brand new. You have brought the hose today, and let's say the owner has not given you a defective one, thinking that, oh, ye to he's a dumb guy. Let me give him a hose which is already cracked. Okay, so unless he has given you this hose, let's say this hose is perfectly fine. There is no leakage in the hose. Okay, so can all of you understand that if, let's say, there is certain mass of fluid which is coming inside, there is certain mass of fluid or mass of liquid which is coming out of the tap, and that water is continuously coming in. Okay, so can everybody understand that if there is a mass of water which is coming over here, and there is water which is going out from here, can all of you understand that if there is a mass flow rate of m dot kg per second which is coming inside the hose, can all of you understand that this same mass of water will be coming out of this hose? This is what is called as continuity equation or conservation of mass. So the first governing equation that we see over here is conservation of mass. Okay, it is one of the foremost equation which is actually used in nozzles. We are going to see that. First we will understand for the nozzles or fluid flow in liquids, then we will put the same laws for the gases also. Okay, so you might see that mass flow rate remains constant. Conservation of mass means whatever is the mass that is coming from here, the same mass is going out. Okay, so this is what is generally happens in case of a duct with constant area where there is no leakage. Okay, so can I say mass flow rate m dot is, let's say, constant, or you can say mass flow rate which is coming out of coming in is mass flow rate which is coming out. So m dot 1 is equal to m dot 2. Now what is the mass which is coming in? Let's say if this fluid which is coming over here has density of rho 1, this fluid which is entering inside, the liquid which is coming inside, is having a density of rho 1, and it is coming with a velocity v1. So can all of you see that the mass which is coming over here, mass is nothing but density multiplied by volume which is coming in, and volume will be nothing but area multiplied by velocity. So can I write m dot will be rho 1 into area 1 into velocity 1. This is the total mass of water which is entering the tube at location 1. Should this be equal to, now what is the mass which is going out? The mass that will go out is, let's say over here, the liquid is coming with density rho 2, area is A2, and velocity is V2. So can all of you see that this should be equal to rho 2 A2 V2. This is what is the first governing equation which actually governs the flow in ducts. Fluid flow in duct. So conservation of mass, which is also called as continuity equation. Okay, in case of liquids, we see that density over here and density over here remain same. So we remove this rho 1, rho 2 because rho 1 and rho 2 are equal. So in that case, area 1 V1 will be equal to A2 V2. That is what is the governing equation of continuity. Is it clear? Understood? So I hope everybody has understood that rho 1 A1 V1 will be equal to rho 2 A2 V2. That is as simple as that. Now, a lot of you might say, sir, this is a constant area duct. So A1, A2 will also be equal. Yeah, I know. If A1, A2 is equal, then sir, V1 and V2 both will be equal. So the water which is going inside the tube at 5 meter per second velocity will also come out at 5 meter velocity. I understand that. I'm not saying what happens over here. We are developing the governing equation, and this is the first equation that I'm telling. We are going to modify this equation. This is what is the beauty that we are going to do. So we have seen the first equation which governs the fluid flow in duct is continuity equation. So we have seen rho 1 into area 1 into V1 is equal to rho 2 A2 V2. Now someone will say, sir, I have fluids, or let's say for liquids. Sir, for liquids, rho 1 is equal to rho 2. Okay. For liquids, rho 1 is equal to rho 2, which is equal to rho, which generally remains constant. So if rho 1 A1 V1 is equal to rho 2 A2 V2, if rho 1 and rho 2 are constant, can all of you see that this equation, rho 1 and rho 2 will change, and this will give area 1 V1 is equal to area 2 V2. So A1 V1 is equal to A2 V2. This is what is the equation which is valid only for liquid. This is valid only for liquids. So guys, you have to be very careful. This is not valid for gases, because in gases the rho 1 and rho 2 can be different. And if they are different, then this will not be same. Okay? Very good. So now you know that A1 V1 is equal to A2 V2. Now let's say this problem was there before the invention of nozzle. Before people invented nozzle, they invented this continuity equation, A1 V1 is equal to A2 V2. Now let's say somebody says, I have to increase the velocity of water. I have to increase the velocity of water which is coming out from this tube. So let's say I have this tube, which is this is a pipe that you have. So I'll tell you how the things develop. You might have made a nozzle. Everybody might have made a nozzle out of this pipe. I'll tell you how. So you see that there is water which is flowing inside this tube. So now you were flowering, or you were giving water to your garden. So there is a water which is coming m dot. There is area 1 which is A1. And there is also water which is coming out. So the water that was coming out of your pipe, it was getting sprayed like this. So you have a pipe and you are giving water in your garden. Now let's say the length of the pipe is such that it is coming till here. So this is, let's say this is your tap. I have the tap over here. Okay, and in this tap, you have opened the cap of the tap, water is coming over here, and from this tap, water is going inside this tube. Okay, so water is going like this. So this length is fixed. Now let's say there is a plant which is kept at slight distance. So let's say there is a plant which is kept over here. You have a flower pot over here, and you have to put water in this plant. There is a very yellowish flower, or let's say this is a marigold plant, and it has given a bud, very yellowish. It's the time of winters, and it is blooming. It has given a very good flower of marigold, and you want to put water over there. What will you do? Tell me first thing that will come to your mind. I know everybody might have done this. So the first thing that you do is you take your hand, one finger, you put it over the front mouth of the pipe, and you block certain passage. I'm sure everybody might have done. So what you actually do is you cover this. You cover this like this. So you have blocked the passage of water through which this water will come. You have put your finger over here. So when you have put your finger over here, this is your, let's say this is your finger. Okay. So you have put a finger over here. Okay. I am sure everybody does like that only. So you put your fingers like that and you will see instantly the water that was coming, or the water which was getting sprayed like this, instantly the velocity of the water changes, and now you see it comes out at very high speed and it is sprayed at a larger distance. Can you think what has happened, or what has actually happened over here? So what has happened is, this area which was earlier equal to A1, now you have reduced this area. So this area A2 you have reduced. So if I apply the continuity equation over here, A1 V1 is equal to A2 V2. Now tell me, if you reduce this area, if you reduce area A2, can everybody understand that by automatically, for application of continuity equation, the velocity should increase? So very intelligently, you have found a way to increase the velocity. And once you have found the way to increase velocity, can everybody understand that you have got a way to increase the kinetic energy of liquid? The kinetic energy is half mv square. So when the velocity increases, the kinetic energy increases. So can we say the devices, or a device or a nozzle can be simply made, by reducing the area of cross section of a duct. So let's say you have a pipe, you reduce the area of pipe, you have a constant area duct, you reduce the area of constant duct. And this is where the invention of nozzle happened. So the people got a very fantastic way to make the nozzles, and what they actually did was this. So what they did is, very gently they designed something like this. This is a simple duct, nothing much. What they did is, very gently they have reduced the area of cross section. And once they have reduced the area of cross section, now everybody can understand that if this is the location, at location 1 where the area is A1 and water is flowing with velocity V1, when the water will be coming out, this will be the area A2 and velocity V2. So you see that since area A2 is lesser than area A1, we automatically know that velocity V2 will be greater than velocity V1. And by doing this simple thing, you have invented a nozzle. And this is what is actually a nozzle, which looks in the liquids. I hope everybody might have understood where the nozzles have actually come from. The nozzles which you see over here, the nozzles which are used in the rockets, have actually come from here. They have been originated from liquids. They have been developed from liquids. And the development is very simple. The application of continuity equation. Okay. So in the same way, when the continuity was developed, people developed the first nozzles which were developed for liquid, and the same application and the same principle was also used for gases. So now let's say if we want to have the same nozzles for gases, nozzles for gases, can we say now we can have the same nozzle for gases as well? Can we say, I hope most of you might have heard that nozzles in case of gases are also like this. Most of you might have heard. Okay. So if we want to see for gases, If I want to see the governing equation for gases for nozzles, can I say the first governing equation will be continuity equation? Continuity equation. So the first equation that we will see is continuity equation. If a nozzle is not leaking, if there is a no mass which is coming inside the nozzle. So if we can apply the continuity equation at location 1 and location 2, can all of you understand that rho 1 into A1 into V1 is equal to rho 2 A2 V2? This is the governing equation. Now you see what happens is, when we are using this equation for gases, we see that for gases, rho also changes. It changes along with area and velocity. So when density changes, let's say you might be having a density of 1 meter cube, 1 kg per meter cube over here, and over here you might be having density of let's say 0.9 kg per meter cube. So the density also changes. So when the density changes, we cannot remove this, and the continuity equation that is governing the nozzles is this. For gases, this is the continuity equation. I hope in colleges or in college you might have studied this as the continuity equation for gases. Okay, so this is the first continuity equation. But if you see over here, simply doing this would not tell you what is the velocity that you can achieve, because now you have only one equation. You have one equation, and you see there are three variables. Density changes, area changes, velocity changes. So now if you control one variable, let's say if you control area, still there will be two more variables left. Let's say area 1 and area 2. You have area 1, let's say this is 1 meter square, and this area 2 is 0.5 meter square. So now you see that area has reduced by half. So now you know that density and velocity has to increase by twice. But which one will increase how much? Will velocity become twice, density remain same? Will density become twice, velocity remain same? Or density will reduce by, let's say, 1/3, and velocity will increase by 1.5 times? It might happen. There will be all sort of permutation combination. So you have only one equation and you have two variables to solve. We cannot solve this. This cannot be solved. This equation cannot be solved. If I give you that area over here and here is 0.5 meter square, let's say the density over here is 1 meter cube per 1 kg per meter cube, and velocity is, let's say, 100 meter per second. Can you tell me what will be the density over here and velocity over here? You cannot solve this, because you don't know what is the governing relation between the two more variables. So we have to develop few more equation. So only this equation is not going to solve our problem. So now what we should do? So to understand this, first we have to understand that what happens in a nozzle. Now we are going to go into the domain of thermodynamics. So in thermodynamics, we are going to study about a lot of equations, but there is going to be one equation which is very fundamental in thermodynamics, that is called as the steady flow. It is called as the steady flow energy equation. Okay, it is called a steady flow energy equation. And you know, most of the students don't truly understand this equation. People say this is steady flow equation which can be applied in these condition. It can be only applied in these condition. But guys, let me tell you, this is the most fundamental equation in case of all fluid flow. Every fluid flow, So you might have heard that the equation that is governing the liquids, if you see the flow of liquid is governed by, some of you might say it is governed by Euler's equation, ठीक है, or few more people might say very more generalized Bernoulli equation. You guys can see, you can say these are the equations which we have been taught in fluid mechanics. When we talk about the fluid mechanics, it is the Bernoulli equation which is there. But guys, let me tell you one thing. This equation is what is the parent equation. Using steady flow energy equation, we can derive Bernoulli's equation. In steady flow energy equation, if you put an assumption that density is not changing, the second equation that you will get is Bernoulli's equation. So this is what is the fundamental equation that is governing the fluid flows. So steady flow energy equation is nothing but it is the equation of, very important, it is the equation of total energy interaction in a fluid. Total energy interaction in a fluid. So this is the equation which talks about lot of energies, or to be very precise, it talks about two energies, or it joins two energies. One is called as the thermal energy. First is the thermal energy, and second it is going to cover mechanical, what we call as mechanical energies. Okay? And when we talk about mechanical energy, there are basically three energies that we talk about. First energy is called as the gravitational potential energy. Okay. Second is kinetic energy. Okay. And third energy is the pressure energy. Energy which is contained in pressure. So this equation is going to talk about gravitational potential energy, kinetic energy, pressure energy, and thermal energy. So when all these energies are combined, or all these energies are taken into consideration, it becomes your steady flow energy equation. Okay. So in thermodynamics, we are going to derive this fundamental equation, though I'm not going to derive it over here, but this equation is applied to most of the flow devices where the fluid flows. So let's say if you have any device, so I'm going to denote a device by a simple block diagram. So let's say if we have a fluid which is entering a device at, let's say, location 1, and it is getting out at location 2. So if this fluid is entering with certain type of energy, which is thermal energy and the kinetic energy, then the different components of the energy, thermal and pressure, when they are combined, they are written in form of enthalpy. Enthalpy is the energy which accounts for thermal energy and pressure energy. Both are clubbed together and this becomes enthalpy. Then we have kinetic energy over here, kinetic energy 1. Then we have gravitational potential energy, which we generally write potential energy at location 1. So a fluid, when enters, it enters with enthalpy, it enters with kinetic energy, it enters with potential energy, and when it is exiting, again same thing is happening, H2, kinetic energy 2, potential energy 2. This is what happens in case of a fluid flow. Now this device which is over here, this device might have interaction with surroundings. This device might be receiving certain energy, or let's say it might be receiving certain heat in the form of Q dot. So let's say any thermal energy which is received by this device, and let's say this device is doing some work interaction also. So there is some W which is going out. It might happen. So there are devices like this where certain enthalpy is coming in, certain enthalpy is going out, there is some heat interaction, and there is some work going on. So you might see compressors. Compressors are the devices which are having fluid flow, and there is an interaction of heat and work over here. There is a turbine. Turbine also has interaction like this. So you see, there can be interactions. And if we talk about the combined energy, then we are going to do energy balance over here. That means energy in, whatever is the energy which is coming in, will be equal to energy which is going out. And if we talk about energy coming in, can we say the energy which is coming inside this device is enthalpy, kinetic energy, potential energy, and heat. So can we say H1 plus kinetic energy 1 plus potential energy 1 plus Q dot will be equal to, so this is the total energy which is coming in. The same total energy will go out, because this equation talks about the conservation of energy. Whatever is coming in is going out. Okay, so if we talk about energy coming in, then the energy that is going out is H2 plus kinetic energy 2 plus potential energy 2 plus W out. And this equation will be applicable to any device which is having a fluid flow. So this will be application to turbines. Okay. This will be applicable to, let's say, compressors. Okay. This will be applicable to any other we will see convergent-divergent nozzles. Okay. This will be applicable to nozzles, which is this will be applicable to fans, which we are going to see in the gas turbine engines when we see the Brayton cycle. At that time, the engines which are running the aircrafts, so whatever is the thrust developed would also be covered by this. In fact, this is one of the central equation. As I said, you can always derive Bernoulli equation from here. That I can tell you now also. So let's say very quickly see how does the Bernoulli equation is derived. So you see, in Bernoulli equation we see that liquid is flowing and there is no heat interaction, there is no workout. And when we talk about the enthalpy, enthalpy is nothing but internal energy plus U1 plus P1 V1. Okay, this is what is the enthalpy looks like. But in case of a liquid flow, you see that the internal energy or the temperature of the fluid does not change. So this remains constant. That means if a fluid is entering with U1, it will go out with U2, and this U2 will be equal to U1. So now if you put, instead of enthalpy U1 plus P1 V1, you put U1 plus P1 V1. You see, there will be a term which is called as U1 plus P1 V1. Similarly, there will be a term over here U2 plus P2 V2, and you know that U1, U2 both will be same, so this will cancel out, and there is no heat transfer, there is no workout, and this becomes your Bernoulli equation. What is Bernoulli equation? Pressure energy plus kinetic head plus potential head is equal to pressure head, kinetic head, potential head. This is what is the Bernoulli equation. Very simple. So you see, the governing equation, steady flow energy equation, is what is the most central equation, and that is actually used in all the flow devices. Okay, so now we are going to see what happens in case of a nozzle. So when we talk about nozzle, so we are discussing about nozzles. So which are the governing equation in the nozzles? So first equation we have already seen, that is called as the continuity equation. Okay, which is continuity equation, which is rho 1 area 1 V1 is equal to rho 2 A2 V2. Okay, now let's see the steady flow energy equation. So when we talk about steady flow energy equation, so if I want to develop this equation for nozzles, so let's say I will again make a nozzle. Okay, so this is my one nozzle, and we are going to see how does the equation look like for the nozzle. Okay, so when we are running the nozzles, we will see that these nozzles are simple devices in which we do not have any heat transfer or we do not have any work output. So in case of nozzles, we have Q dot is 0. Similarly, work output is also 0. The main purpose of a nozzle is to increase the velocity of fluid. So a fireman who is using the nozzle, do you think it will transfer heat inside the nozzle or it will take heat out from the nozzle? No. Do you think that nozzle will be doing certain work? No. So there is no work or heat interaction. So if there is no work or heat interaction, let's say there is a fluid or there is a gas which is entering it, and it is entering with enthalpy H1, it is entering with kinetic energy K1, it is entering with potential energy P1, and then it is going out with enthalpy H2, it is going out with kinetic energy K2 and potential energy 2. And you see, when there is no heat interaction, we actually describe this nozzle as adiabatic. Adiabatic means there is no heat interaction, and adiabatic is generally described like the lines like this. So this tells you that the nozzle or the device is working as adiabatic. Okay. So now if we want to understand the governing equation over here, can I say for this nozzle or for nozzles, can I say H1 plus kinetic energy? So you see this H1, this is a smaller quantity. So we are taking the mass flow rate as 1 kg per second. Let's say mass flow rate we are taking as 1 kg per second. So when we talk about the enthalpy, there are two terms of enthalpy which we define. H1 is called as the specific enthalpy, which is enthalpy of 1 kg of fluid. And there is a bigger part of this which is written by capital H. Capital H is nothing but mass flow rate multiplied by the specific enthalpy. So if we are talking about 1 kg fluid per second, okay, so in that sense, the enthalpy is H1 for 1 kg. Now the kinetic energy is written as half into m into v1 square. But since m is 1 kg per second, we are going to remove the m and it becomes v1 square divided by 2. H1 plus v1 square divided by 2 plus potential energy. Potential energy of any fluid is written as m into z into z, where z is the datum head. That is the distance over the surface of Earth. So let's say this device is sitting over here, which is at a distance z1 from here, from the Earth's surface. So you see there might be a rocket which is flying at certain altitude, so it will have certain potential energy. Okay, so then you can write m into g into z, but since m is 1, so you can write zz1. Okay, that should be equal to, because now there is no term of q dot, so that should be equal to h2 plus v2 square by 2 plus zz2. Okay, so this becomes your continuity equation. Okay, so now when we say h1 plus v1 square by 2 plus zz1 is h2 plus v2 square by 2 plus zz2. Now if you see one term over here, we see that the nozzle which is kept like this. If you see from ground, the center of this fluid or center of this nozzle is at certain height. Okay? Similarly, if we see from here, the center is at certain height. Can all of you see that in most of the cases, this height h1 and this height h2 both will be same. There will not be much of difference. So if a nozzle is kept in, let's say, horizontal direction, even if it is in vertical direction, it will not make much of the difference. I'll tell you later why. Okay, but if I am assuming the first assumption we are putting over here, if z1 is equal to z2, so if z1 is equal to z2, can we remove these two terms? Okay, So in that case, our steady flow energy equation becomes H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. This is your second governing equation. So this equation is the equation of energy which contains enthalpy. Okay, and we know that if there is a fluid or if there is a gas which is moving in the nozzle, so the enthalpy plus kinetic energy will be equal to enthalpy plus kinetic energy 2. So from here, can I write H1 minus H2 is equal to V2 square by 2 minus V1 square by 2. And this can be written as H1 minus H2, which is V2 square minus V1 square by 2. So this represents change in enthalpy. This represents change in enthalpy. And see, enthalpy is nothing but it is a sort of energy. We are going to see that this represents change in kinetic energy. Okay. So you see that whatever is the change in enthalpy, whatever is the drop in enthalpy in the nozzle, whatever is the energy that has dropped in form of enthalpy, the same energy is reflected in kinetic energy. So these two energies are getting interchanged. These two energies are getting interchanged. One energy is going into the another. So you see, if a fluid is moving in this direction, it becomes a nozzle. If it moves in opposite direction, kinetic energy will get changed into the potential energy. Not potential, enthalpy. This becomes a diffuser. So this is a second type of device which is working on the same principle. Okay, so this is what is the second governing equation. But now if you see, the second governing equation is H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Okay, this is the second equation. Okay. Sorry. What was our first equation? So this is the second equation. What was our first equation? First equation was rho 1 into area 1 into V1 is equal to rho 2 into area 2 into V2. Okay. So what are variables over here? You see that in terms of variable, first we have seen that there are three variables: density, area, velocity. So these are the three variables. You can control them. Okay, you can change any of them. What are the variables over here? There is one more variable that you have introduced, and that is enthalpy. How many variables are there now? So you have total 4 variables. How many variables? You have 4 variables. Out of those 4 variables, you can control one. Okay, so you can control one. So let's say if we control one variable, how many unknowns are there? There will be 3 unknowns. Now if you want to get the values of all this, if you want to get the values of rho 1, area 1, V1, H1, and rho 2, area 2, V2, H2, if there are 3 variables, you will require how many equations to completely solve it? You require 3 equations. But how many equations are there? You have only 2 equations. So can you solve the problem? No. Again, the same thing happens, that though we have increased one equation, though we have got one more equation now, but there is one more variable that you have introduced. So you cannot solve this equation. Even if you define over here that for a nozzle, rho 1 is this, area 1 is this, or velocity V1 is this, and my area A2 is this. Now tell me, what is enthalpy over here? What is density over here? What is velocity over here? Nobody can solve this, because there are 3 variables over here. area you have defined, you have to calculate enthalpy, kinetic energy, and density. And these three variables can only be solved with the help of three equations. So you will need one more equation. We need to have one more equation that can govern this fluid flow. So to understand the third equation, we are going to develop the third equation. But before going for third equation, let's reframe this equation, the steady flow energy equation that we have got. So if we reframe the steady flow energy equation, we see that the steady flow energy equation has turned into H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. And you know that for gases, enthalpy is a function of temperature only. Enthalpy is a function of temperature only. That means if you define temperature of a fluid, the automatically enthalpy get fixed. And what is that relation? You know that enthalpy is nothing but it is equal to Cp into T, where Cp is specific heat capacity at constant pressure. Okay, so H can be written simply as Cpt. Now how this comes, this we will see later. When you are going to study the basic thermodynamics, we will see this, but since all of you are aerospace students, you might be already aware that enthalpy and internal energy are functions of temperatures and specific heat at constant pressure and constant volume. Understood? So now I can change this, I can put this H over here, and this becomes Cpt1 plus V1 square by 2 is equal to Cpt2 plus V2 square by 2. So this is the second equation that we use. So steady flow energy equation is used in this form. Cpt1 plus V1 square by 2 is equal to Cpt2 plus V2 square by 2. Okay. So now we have seen the second equation, and now we have to develop one more equation. So when we want to develop the third equation, we have to understand what is happening inside the nozzle. So if I tell you what happens in a nozzle, so from the fluid mechanics or from the liquids, you might have already idea that what happens in case of a nozzle. So in case of a nozzle, let's say I have a nozzle over here, you will see that there will be a high pressure. There will be a high pressure gas which will be available over here. And when this high pressure gas moves, its velocity gets increased. So if you see in the Bernoulli equation, if you apply the Bernoulli equation for liquids, you will see that when the pressure is getting or when the velocity is getting increased, the pressure reduces. The same thing happens over here also. In case of nozzles, this is a high pressure. You will see at the exit there will be low pressure. Okay? There will be a low pressure gas coming out at high velocity. So pressure energy gets converted into the kinetic energy. So when there is a pressure changing, can you see the gas which was at high pressure over here, the gas which was compressed, the gas which was under high pressure over here, now this will expand. Now the pressure increases, pressure reduces. So whenever the pressure reduces, the expansion of gas happens. Okay, the volume of the gas increases. Okay, so when the volume of gas increases, which is the governing equation which governs this expansion or compression? So the expansion or compression is governed by different laws of thermodynamics. So there are different processes in thermodynamics. If we see, there are 4 processes in thermodynamics which happens. Okay, first one is constant volume process. there is a constant volume process where the volume of gas remains constant. ठीक है. Second process is constant pressure process. Constant pressure process. Third process is constant temperature process. Constant temperature process. So these three processes will have one of the properties constant. So we know that gases are generally governed by PV equal to mRT. This is the governing equation for all the gases. So if you see the gases, they have pressure, volume, temperature, and mass. This is the core governing equation which governs the gases, which is called as ideal gas equation. Okay, any ideal gas will follow this, PV equal to mRT. Okay, so now you know that PV equal to mRT, if I have a constant volume process. So let's say there is a constant volume process happening. So in the constant volume process, pressure will be directly proportional to temperature. Second is constant pressure process. In the constant pressure process, volume is directly proportional to temperature. And third one is constant temperature process. So if temperature is constant for that gas, PV will vary inversely to one another. PV will be equal to constant. And there is a fourth process also, which is called as isentropic. So isentropic process is what? Which has entropy constant. So there is a property which is called as entropy. You are going to understand it in basic thermodynamics, that what is the true sense of entropy. Okay, so when we say entropy is constant, now how does this entropy is governed over here? So you don't see any entropy term over here. So how you are going to keep the entropy constant? So this entropy constant happens when the governing equation is PV to the power gamma equal to constant. So the reversible adiabatic, a process which is moving as reversible and in which there is no heat interaction, this process is what is called as isentropic process. And this process is when the process happens like very fast, all of a sudden. So if there is a gas which is compressed at extremely high speed, it occurs at such a speed that you do not let the heat transfer happen. If there is no heat transfer happening, then this process happens, PV to the power gamma equal to constant. This is called as isentropic process or reversible adiabatic process. Now if we see our nozzles, you see in case of nozzles, when the fluid is moving, the fluid moves at very fast speed. It moves at extremely high velocity. It moves at extremely high speeds. That means there is no time which is occurring for expansion or heat interaction. The moment the air is over here, zoom, it'll be over here. It'll be out of the nozzle. So this process becomes extremely fast. So if the process is becoming extremely fast, then the process of expansion or process of compression which is happening in these devices, which happens in adiabatic devices, if the process is reversible, then they will be governed by the third equation, that is called as, the third equation is PV to the power gamma equal to constant. Okay, and this is the third governing equation which governs the nozzle. Now if you see how many equations are there and how many unknowns are there, so you'll see that the first equation, rho into area, rho 1 area 1 V1, or you can simply write rho into area into velocity is constant. Okay. The second equation is Cp into T plus V square by 2 is constant. So now you see how many variables are there. There are variables are variables are, you have density, you have area, you have velocity, and then you have another variable that is volume. This is V. So PV to the power gamma. Okay. You have volume PV to the power gamma. Then you have pressure. Okay. So you have so many variables. And then last one is temperature. So you have 3 plus 3, 6 variables. Okay. And these 6 variables now have to be solved. Okay. So how many equations you have? You have rho AV CPT1 V square. Then you have PV to the power gamma equal to constant. Okay. There is one more equation that we have already seen, that is ideal gas equation, PV equal to MRT. Okay. So P into V is equal to MRT, which is another equation. So you have 4 governing equations. Okay. And out of these 4 governing equation, you have to solve for these variables. Okay. So using all these equations, we solve for these variables, and you will see that these can be directly solved. Okay. Out of these variables, velocity, volume, pressure, temperature, and density. Okay. Density is also taken care by over here. P, or we can directly write P by rho. Though you can write this, but P by rho is equal to RT. You can write it in this form as well. Okay. So using all these 4 equations, we solve these variables. Though we provide certain inputs over here. So we provide area, we provide pressures. Okay. Generally we provide for some of these values, and then we solve for. Okay. So now let's see, we have a nozzle. We have a nozzle. And for that nozzle, how do we solve? What are the different velocities that we get, and how we come across? So to understand this completely, though these are 6 variables, and these are 4 equations also. These are 4 equation only. We cannot completely solve them. We will require one more equation to solve for these variables. And that equation also we will see, but that equation we will not derive over here, because that equation actually governs about the area, velocity, and density. Okay. So this, the 6th equation also we will derive. There is one more equation, that is C is equal to under root gamma into R into T. This is the equation of speed of velocity, or speed of sound in a gas, but it will introduce one more variable, that is C. There will be one more dimensionless variable that will be coming into the picture, that is M. M is the Mach number. Okay. And that Mach number will have one more equation, V by C. So this is the 6th equation, but now the variables are 8. So still we will require one more equation, and that equation, the 7th equation, will be equation of area. Okay. So that equation, the derivation is slightly longer. So we are not going to derive that equation, but out of these equations, out of these variables and whatever the equations are over here, we are going to solve for certain quantities. Okay. So let's start with the first variable that we see. And the first variable that we are going to see, or the first equations that we are going to see, is through the flow of gases through nozzles. Okay. Gases through nozzles. Okay. So when we see, there are generally 2 equations that we use. So the first equation that we use is CPT plus V square divided by 2 is constant. This is the first equation that we use. And the second equation that we use is PV to the power gamma. PV to the power gamma is equal to constant. So if you guys might have studied PV to the power gamma equal to constant. This equation can be applied at 2 point in terms of temperatures also. So PV to the power gamma equal to constant can be applied in form of TV to the power gamma minus 1, or it can be applied in form of pressures. Okay, so from here we can see that T2 by T1 can be written as P2 by P1 ki power gamma minus 1 over gamma. This is one relation that we are going to use for these gases, okay, when they are flowing through a nozzle. Okay, so now let's start with this equation. So let's say we have a nozzle, and through that nozzle there is a fluid flowing. Okay, so at location 1, let's say we define temperature T1, we have pressure P1, we have velocity V1. Okay, so we have velocity V1. Now there is a fluid, there is a nozzle through which the expansion happens, and the temperature goes to T2, pressure goes to P2, and velocity goes to V2. Okay. So now using these variables, you can use steady flow energy equation. So when we have steady flow energy equation, we can apply that steady flow energy equation is H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. This can be written as CPT1 plus V1 square by 2 is equal to CPT2 plus V2 square by 2. Okay, and now you see that we can divide this whole equation by CP. So dividing by CP, we see that this will become T1 plus V1 square divided by 2CP is equal to T2 plus V2 square divided by 2CP. And from here you can write T1 is equal to T2 plus V2 square minus V1 square divided by 2CP. Understood? Okay, I hope everybody understands this. Okay, so in case of, if you want to write in terms of temperatures also, you can write T1 minus T2. If you want to write T1 minus T2, then it can be simply written as V2 square minus V1 square divided by CP. Okay, so let's say if you have a nozzle, in which it is given that at one location the temperature is T1 and at another location the temperature is T2. If at one location velocity is V1, then you can automatically find what will be the velocity at location 2. So let's say we can simply say, if we write question 1, so let's say a gas or air is expanding, or air expands through a nozzle with following data. Okay, so it is expanding with following data. So at entry we have temperature T1 is, let's say, 500 Kelvin and velocity V1 is, let's say, 10 meter per second. Okay, now when the air is coming out at exit, the temperature T2 is, let's say, 400 Kelvin. Can you find what will be the velocity at exit? What will be the velocity? So you can very easily calculate what will be the velocity. So you know that T1 minus T2 will be equal to V2 square minus V1 square divided by 2 into Cp. Okay, and you can bring this 2 into Cp onto the left hand side. So T1 is 500 minus 400 multiplied by 2 multiplied by Cp for air is 1005 joules per kg Kelvin. That will be equal to V2 square minus V1 square is, V1 is 10 meter per second, so 10 square. Okay, so this will become 2 into 100 multiplied by 1005 is equal to V2 square minus 100, and from here you can calculate V2. So the value of V2 will come out to be value of V2 will be 2 into 100 into 1005. So 1,05,000 plus 100, okay, and square root of this. So power of 0.5. So 317.7 meter per second. Is it clear? So it is as simple as that. So you see, now you have developed, or now you have found out a way of calculating what is the velocity at exit of the nozzle if the temperatures are given. Okay. So now let's say if somebody gives you P1 also. He says the pressure P1 is if P1 is equal to 10 bar. Can we calculate P2? Can we calculate P2? Yes, we can also calculate P2. How? Because we know that the flow which is moving through the nozzle is isentropic. So if the flow is isentropic, can we write for isentropic flow? For isentropic flow, we have P2 by P1 is equal to T2 by T1 की power gamma over gamma minus 1. Okay, so this you can calculate P2 divided by P1 is 10, that is equal to T2 is 400 divided by 500 की power gamma is 1.4 divided by 0.4. So from here you can calculate P2. What will be the value of P2? So quickly, those who are very fast on calculations, 0.4579. So 10 multiplied by 0.4579. So you will see that it will be 4.579 bar. I hope you understood. Okay, so it is very simple. I hope everybody has understood. You can calculate if you are given density at location 1. If you are given density at location 1, whatever is the density, let's say 2 kg per meter cube, though it will be there. Okay? So from here you can calculate by using PV or P by rho is equal to RT. So P2 by rho 2 is equal to RT2. So from here you can calculate density rho 2. Rho 2 will be equal to P2 by RT2. You can simply calculate that. Okay. So if you are given density also, you can use all these formulas for calculation. Okay. This equation can further be enhanced, or the same equation that we have developed, the temperature equation that we have developed, can also be used for calculating what is the Mach number. Okay, so since we have calculated velocity V1 at location 1, or we have found the location velocity V2 at location 2. So since we know the velocity V2, since we know the temperature T2, from here we can calculate what is the velocity of sound. So C2 can be calculated as under root of gamma into R into T2. So from here, once you calculate the C2, and from that C2 you can calculate the Mach number, which is V2 divided by C2. So guys, we see that every equation, we can solve this whole equation with the help of whatever we have developed. I am sure you guys might have understood the concept well. So for your homework, I want to give one question. So it says air enters a convergent divergent nozzle. For the time being, you don't have to worry about what a convergent divergent nozzle is. The only thing is that you are given certain data. So at entry, it is 5 bars and temperature of 900 Kelvin. Okay. So at entry, the temperature is 500 bar and pressure is 5 bar and temperature is 900 Kelvin. The exit velocity of the air you have to find if it is discharged to the atmosphere at pressure 1 bar. You can assume velocity v1 is equal to 0. So I would request all of you to do this question. So first what you have to do is you have to use pressure of 5 bar and 1 bar. Then from those pressures, you have to find what is the temperatures at location 1 and 2. Location 1, it is already given. You can find the temperature at location 2. And once the temperature is calculated, then you can simply use that temperature in the equation, energy equation, to find what will be the velocity. Okay, I hope all of you will be able to do that. Okay, so guys, that's all what we have or what I have for today. This was very basic lecture on nozzles. We are going to study it in a much more detailed way. Though I have given you a glimpse of the nozzle, I have to give you a very crisp so that you can get an idea on what is the level of the teaching that we are going to provide. So I am sure you might have loved it, and we surely look forward to have you guys taking the courses, GATE Wallah courses, GATE Wallah Aerospace courses, and learning everything in detail. Okay, and I hope you liked this lecture also. I'll be uploading more lectures on YouTube for some of the core concept, like I will upload the lecture for thrust, how a thrust is developed, how what is the application of Brayton cycle. So we are going to see the Brayton cycle videos also. Okay, so there are going to be already the lectures coming. So Bansal sir is already taking up your vibration lectures. Approve sir has taken your strength of material lectures, and Shivam sir will also be taking. So guys, stay tuned for more lectures, and do let us know. So in the comment section, if you watch this lecture, do let us know how did you find these lectures, because it will also help us in understanding what are your expectations. Though we are confident that whatever we are teaching, nobody has taught you till now, but still we would like to hear from you. If you like this video, then do let me know that how was that you liked the video and what more content you would like to learn. Okay, so with this, thank you so much. See you in next video.